CE for their hard work, or the student executives for their hard work, because they have been putting a wonderful publicity. So thanks to them, thanks for their hard work. Over to you, Professor Chakraborty, now.
Okay, thank you for the very long introduction. I don't think I deserve such a long introduction, but in any case, uh, I will share the screen in a little while. But first of all, it is really an honor for me to be giving this talk. Many of you will not know. I mean, I did my PhD in 2017, and Professor Hajira was talking about Professor Orunasis. So he was actually my examiner. So yeah, he was the one who reviewed my thesis. So it's an honor actually. So yeah, I will be talking about physics information learning. Professor Hajira said so many things about physics information learning. I hope by the end of the talk today, you will realize that it is nothing. The term may be new, but the concepts are not new. Neural network may sound new to you, but it's the same thing, linear algebra statistics. And hopefully by the end of my talk, that will be clear to everyone. So let me share my screen and start with the talk basically. So I hope my screen is visible. Uh, can you please confirm?
Yes, you are very much visible to me. I may want to take a few confirmations from the others.
Yes, yes, it is visible.
Yeah,
Okay,
thank you, Professor
thank,
Das.
thank you. So okay, so what I will be talking about is actually one of one of my recent research paper, and the title is already shown here. I want you to focus on three terms here. One is transfer learning. I will talk about it in details. What I mean by transfer learning. That is a generic term, nothing new. Second thing I want you to focus on is obviously physics informed deep neural network, and that will be I will be talking about it significantly. And the third thing here is multi-fidelity, which means data of different accuracy. It can also mean physics or model of different accuracy. So if you're talking about finite element, if a coarse mesh will be a low fidelity and a fine mesh will be high fidelity. I mean, that is how this terminology is generally used. Now, before starting my talk, let me give you some background on this. So I was actually at UBC. I got the offer from IIT Delhi. I I left the job there, and I was supposed to join in IIT Delhi or join IIT Delhi as a faculty, but then COVID happened. So I could not join. It was delayed and I was at my home doing nothing. And that is when this idea came to my mind. Now, everyone who works on deep learning know that, that if you are working on deep learning, one thing that you will need is GPU. Without GPU, computation is very difficult with deep learning. But I was at my home with no GPU access. Forget not even a computer. I have my Apple MacBook Air, which is not sufficient. So I did all of this in cloud. Actually, Google Colab provides some cloud computing resources, very minimal, but that's what I used, and I did this. And as a result, you will see that the problems that I will show, which is towards the end of the talk, are kind of small scale by my standard. And that is basically the reason. But this was a story. But then, yeah, but then this gained lot of attention, this work. So that was quite nice. So I come from a civil engineering background. So my BTech is in civil engineering, my master's, PhD, everything is in civil engineering. But if you classify me by my work, I consider myself to be a mechanics person or someone from a mechanical science background. And that means both mechanical and civil, basically. So I will be talking about mechanics. So physics for me means I'm talking about mechanics. And we know that physical systems are governed by physical laws. And this is well established. I'm not saying something new. This is well known. So I have shown here two figures. On the left, there is a bullet which is going past or which is penetrating a plate. And you can see that as it is penetrating, there is fractures and all those things happening. So this is basically an impact problem. On the right, we have a wind turbine. Wind is going past the wind turbine, and there is a flow field that you can see. And in both of these cases, these are real life problems, but these are governed by very well defined physical laws. And when I say physical laws, I refer to the governing differential equation. In practice, if you try to solve it, it may take you days, if not months, to run this simulation. That is a different story of its own. But the point I'm trying to make here is that physical systems are generally governed by physical laws. But the question that we need to ask is, are the physical laws exact? So let me give you one very quick example. So we know about the stress equilibrium equation, and that is kind of exact. But what about the stress strain relation, the constitutive relation? You assume the material to be linear elastic, or you assume some parametric model and try to fit some data to it, right? So which means this is often not exact, the material model. Similarly, strain displacement relation, often we work with the small strain, small displacement or small deformation assumption, and we end up using the relation epsilon is equal to half grad u plus grad u transpose. That again is an assumption. And then boundary condition, initial conditions, knowing them exactly is not that straightforward. I mean, you can probably never have something which is simply supported in a perfect manner if you try to do an experiment. So although physical systems are governed by physical laws, the physical laws are not like they are exact. There are assumptions and approximations that are there, that are hidden, and without those assumptions and approximations, we will probably not be able to arrive at those laws in the first place. So the question we are asking here is that if we have some physics using which we can actually solve, and then if we have some data also, because we are going to talk about deep learning, so what can we do with both of these quantities? So let us first think of the challenges, and then I will provide the problem statement in a precise manner. But the challenges are governing physics is often not exact, and that is what I was trying to illustrate with the example in the previous slide. The boundary conditions, for example, may not be approximate, and these two reds are related to the physics of the problem. You can think of data that, okay, I can collect data, I can do a machine learning thing. Well, that's not straightforward. Data collection is very expensive. I mean, if you think of collecting data by running this simulation on the right hand, top right, well, very difficult. One single simulation can take days. And so how much data can you collect? You will have to work with sparse data. And then the data you are going to collect, it may be of multimodal nature. And if it is of multimodal nature, if the data is coming from some multimodal distribution, then you are in, and that is not an easy problem to solve. Obviously, the data will be having some noise, and there may be outliers, and those problems are obviously there. So these are the challenges. These are some of the challenges. And the idea is, what can we do? How can we bring these two spectrum, one governed by physics, one governed by data, together so that we can have the best of two? I mean, you take the best thing from the physics, you take the best thing from data, and how you can bring both of them together. And that is kind of the motivation here. So, and the question we are asking is, can we leverage recent developments in the field of machine learning to tackle these issues, the issues highlighted in red related to physics and in blue related to data? So now, before I proceed with the talk, I will like to talk very briefly about neural network. Now, me being a person from mechanics working on machine learning on neural network, I have come across people who think that, who treat machine learning as or deep learning as a black box, and think of it as some black magic that you give some data, it will do some magic and it will give you some result. Well, it does not work like that. It's not a magic. There is some mathematics there, right? So let me just very quickly go through it. So in a neural network, it's very simple actually. It's a nonlinear mapping, period. It's a nonlinear mapping, and that's it. So we do linear regression, it is a nonlinear regression. You have some inputs. So these are your inputs, X, you can think of it, and you have some output on the right. And then what you do is you pass this input through some nonlinear functions. So F1 is a nonlinear function, F2 is a nonlinear function, F3 is a nonlinear function, and that's what you do. So you end up getting a composite nonlinear function. And that is what neural network is. Nothing more, nothing less. Neural network is a composite nonlinear function. Now, how this function is represented, we need to parameterize it somehow. And this function is parameterized by the form that is shown here. So you have a linear mapping here, W transpose X plus B. You can call W the weights, B the biases, X is your input. I'm talking about H1 here. And then there is a nonlinear function. This is known as activation function. And this is known as activation function because neural network was initially developed for classification. And so it was like activating a neuron if it is 1 or deactivating it if it was 0. So something like that was initially thought of. But in essence, it is basically a nonlinear function. It can be a tan hyperbolic function. It can be a sigmoid function. But this is a nonlinear function. And each of this is a nonlinear function. So we are dealing with a composite nonlinear mapping from the input to the output. Obviously, these weights and biases are unknown, like in linear regression. You want to minimize, you want to find them. If you have enough data, you can go ahead and minimize the difference between your actual and the predicted in some statistical sense. You can minimize the negative log likelihood or maximize the likelihood. You can minimize the mean square error or whatever loss function you want to define. You are free to do that depending on the problem at hand. So this is nothing. The take home message from this slide is neural network is nothing but a nonlinear composite function. And it is trained by solving an optimization problem. So that is what a neural network is. Yeah. So that's what it is, right? A nonlinear mapping between the inputs and the output. Now, coming to the core of the talk today. So what I will be talking about, that was like a precursor or a brief flavor of what I work on and what I'm going to talk about in some sense. So first of all, I will talk about the problem statement, where I will basically specify exactly what we are looking at, what kind of problem we are looking at, what are different fidelities, and where is physics informed coming into picture, what is physics informed. So those problem statement will come here. I will talk about PIN, that is the physics informed neural network, because that is the backbone of the proposed framework. And then I will talk about some hypotheses. So we talk about learning. So what is learning? What is knowledge? And how you can preserve knowledge? And all this in the context of deep learning. So I'll talk about what is knowledge, how you can preserve knowledge, not in the literal sense, but kind of like comparing with real life and deep learning. And then we will go into the proposed framework, which is basically a combination of the hypothesis and the pins. I'll show some examples. And then finally, I'll talk about way forward. I mean, limitations. I mean, it's not perfect by any sense. There is much more that needs to be done. I mean, it's not perfect. So I will talk about that finally. So let us start with the problem statement. And to define the problem statement, let me define some variable. So you see capital Z is here. Capital Xi represents stochastic variables. So we are dealing with uncertain domain. There is uncertainties in the parameters. And those uncertain parameters or the uncertain variables are denoted by capital Xi. And if you draw samples from this capital Xi, you will end up getting small xi, which is a realization of your stochastic variable. We will talk about reliability. And in the context of reliability, we need to define limit state function. So limit state function, for those of you who are not from reliability background, well, limit state function is nothing but a function that defines a boundary between failure domain and safe domain. So if it is on the, it is basically the classification boundary. If you are on one end, that is a safe domain. On the other end, it is a failure domain. You can think of it like that in a simplistic manner. So I was talking about failure domain that is denoted here omega f z, and that is denoted by all those z's corresponding to which the limit state function is less than 0. So that is my failure domain. And then you will need CDF because there is uncertainty. So CDF, PDF, you will need those things. So capital F is basically denoting your cumulative distribution function, which is your CDF. Now we are interested in some system, right? Some physical system. And the physical system will be governed by some physical equation. So for the physical problem we are interested in, you can consider it to be your a generalized governing equation of the system, obviously approximate because this equation has been arrived based on certain assumption and approximation. And the objective is, given that there are some uncertain parameters, capital Z, what is the probability of failure? How to compute probability of failure? So that is kind of the objective here. Now, this equation that you see here, this is approximate and based on assumption and approximation. And so I'm going to consider it as my low fidelity model. This is my low fidelity physics or low fidelity model. Moving ahead, I also assume that I have performed some experiments in some lab or I have collected some real life data. I placed some sensors for collecting data. So X is basically my sensor location. And then there are time instants at which I have measurements, and I have measurements corresponding to different stochastic variables. I mean, different realization of the stochastic variable. So if I have to compute what is my data, then this is my data, the combination of these three. So, and I am calling it my high fidelity input data because I think I trust my my on-field data more than my simulation model. Now, if you're doing experiment and you know your experiment is not that accurate, you can reverse it. That's also fine. In that case, you will have low fidelity data and high fidelity physics, but that's not what we are trying to do. What we are trying to do is that we have data of sufficient accuracy. The physics is having some approximation. And then the question we are asking is how to combine the low fidelity physical law and the high fidelity but sparse data and use it within the deep learning framework for accurately computing the probability of failure. So by this question, we have constrained ourselves. Since we have constrained ourselves to the low fidelity physical law, so that means I cannot directly use the governing physics to generate data and train a model or to train it directly from the physics by using physics informed neural network. Because this is low fidelity, you will get wrong result. As for data, if you have enough data, you don't need physics probably in many cases. But I am saying that I have sparse data. So the data I have is very few. And as a result, I cannot directly train a model because my data is very sparse. So now that is a challenging scenario. You cannot do either of that. You need to fuse them somehow. And that is the thing. One more thing we are assuming is that the physical law that is given here. So basically this law, although this is an approximate law, this is non-trivial to solve. This is computationally expensive. So it's not like you can generate enough data by solving that physical law easily. Although those data may be low fidelity, but even in that case, that is also not available. And this is actually a realistic assumption. For example, if I look into fluid mechanics, people use alias. Alias takes a hell lot of time, but alias is not exact. I mean, DNS is more exact, and maybe even more exact is the experimental results. So you can think of it as an alias model or something like that. Even you can think of MD, molecular dynamics, can be a low fidelity model if your DFT, if you consider DFT, that is kind of your high fidelity in that case, in the materials point of view. And obviously the other thing I've already told you. So these are the two constraints that we have put into place. So now let us come into the physics informed part. Now, let us assume now that what if my physics was exact? And let's say my physics is exact and it is of the form shown on the top right. If you follow my cursor, you will be able to see it. So this is my governing physics. And let's say it is exact. And I want to represent it using a neural network. How can I do it? And this is where physics informed neural network comes into picture. Now, some of you might be thinking that, OK, this is exact. I can solve it, generate data, and based on that data, I can train a neural network. Yes, you can do that. But in that case, you are learning from data. And there is no guarantee, although the data is generated from this, the governing physics will actually be satisfied. The gradients of the data, for example, if you're solving for displacement, the velocity may not be correct. If you're only training for displacement and time as input and displacement as output. So that has some challenges. And this is what motivated to develop what is known as physics informed neural network. So first of all, physics informed neural network, the term was coined by George Karniadakis in a paper published in 2019. But actually the concept was not his. The concept was there, dormant. It was proposed in 1992. And after that, in 1993, there was another paper, and then no one used it for 25 years or 26 years. And then Karniadakis revived this with modern computational technology, and then it became popular. But the actual foundation of the method was laid in the 1992 paper. So here is the idea. Forget about neural network. I have an equation. I want to solve it. What can I do? What I can do is very simple. I can represent u by using some basis functions in t and x, a naught plus a1 t plus a2 x or a naught t comma x or something like that. I can represent u as a linear combination of basis function, compute the gradients, substitute it back into the equation. I will get my residual. And I can minimize my residual by generating some collocation points to compute the unknown parameters or unknown coefficients associated with the basis function. And this is what was done in the pre-FE era, right? And we are doing exactly the same thing. We do here exactly the same thing. The only difference is instead of basis function, now I have a neural network in place. So previously, if you x and t were my input, so u was related to x and t by using basis function. Now u is related to x and t by using this feed forward neural network. Okay, so that is what we are doing. Next step, we need to compute the gradients with linear basis function. It is very easy. In this case, it is a nonlinear composite function, so not so easy to compute. But you can do it, right? It's not impossible. You can use the chain rule and you can compute del u by del t, del u by del x, and you can compute all the higher order derivatives as well, as long as you need, given that you have selected your nonlinear activation function properly. So in 1992, they were really hardworking people, right? So they did it by hand. They sat down with pen and paper and calculated these things by hand. In today's time, we have become lazy because we have more resources. So these gradients that I'm talking about, you don't need to compute them by hand. There is something known as automatic differentiation, which uses the chain rule and do it for almost no cost or some cost, but for free, and those are exact. So you can directly compute it using del u, using automatic differentiation. And I will show you later that this is actually embedded within the standard packages, not packages, I will say libraries of neural network that you use nowadays. So, okay. So what we have done till now is we have taken x and t, represented u using a neural network where the input to the neural network is x and t. And I have told that we can take derivatives of u with respect to t, with respect to x by using automatic differentiation. So now I have all my ingredients. So what I will do is I will take all the derivatives which is needed, substitute into the governing differential equation, and I will have my residual. And that is what is shown on the right hand side. So right hand side is actually representing the residual R. You see here? And this is what I call the physics informed neural network, because this is constraining the neural network to satisfy the physics, or it will be used to constrain the neural network to satisfy the physics. So this is my physics informed neural network. Now what you can do is you can generate random points of x and t. At all those points, your residual ideally should be equal to 0. So you can define a loss function using this R, which forces each of those R to go to 0. And you can compute the weights and biases. The nice thing here is when you take the derivatives, the weights and biases do not change, because weights and biases are not function of t and x. So this network on the left and the network on the right share the same parameters. And that is exactly what is shown here. So x and t is being mapped to you through a neural network f theta, where theta is my parameter. And then in this physics informed case, x and t is being mapped to r through this residual. And you see the parameters are the same. The parameters are not changing. So that means once you compute, or you can obtain the parameters from the neural network on the right, and those will be the exact same parameter from on the left. So now if the parameters are not changing, what has changed between these two neural networks? Remember the activation function, the nonlinear function? That is what changes. Sigma is what changes. So that's what changes when you take the derivatives. So this is what we do. Now this is my loss function. You see there are two components, LP and LD. So LP is my physics informed loss function, and you can see here I'm taking mean square of this r theta, which means that each of these r theta will be pushed towards 0, which means it will push towards the actual solution, although it will never be 0 in practice. So you will obviously be satisfying the physics in an approximate sense. Obviously satisfying only the physics is not enough, because you have to satisfy your boundary condition and initial condition. So for that, there is another component of the loss function, and this ensures that your neural network output matches the initial and the boundary condition. Now there may be case where you have also some experimental data. Nothing to worry, that is good actually. In that case, put every data you have into this LD. So that means this provides you a tool which can help you to seamlessly travel between physics and data. You can have a situation where there is only physics, no data. That means only boundary condition, initial condition, physics. You can have a scenario where there is both physics and data. And obviously, there can be a scenario where the physics is not known. And in that case, this will revert back to the usual data-driven framework, right? But this thing we cannot directly use. You cannot hope to use it directly, because if you try to use it directly for our problem, remember that for us, the physics is approximate and the data is kind of high fidelity, not exact, but high fidelity, right? So in that case, if you put those two things which are not in synchronization with each other, this loss function may never converge. So if you're thinking that you can put physics here, data here, well, that is not going to work. This will only work when data and physics are of equal accuracy level. If they are not of equal accuracy level, then you are in trouble. I mean, you cannot use this. Okay, now that was a conventional differential equation we are talking about. Only x and t was my input. But the problem we are trying to solve is having some uncertainties. So there is some uncertain parameter also. So you can think of elastic modulus as uncertain, let us say. So in that case, what you can do? Well, nothing to change. You have one additional parameter. The xi parameter is also your input now. That's it. And all the red connections you are seeing, those are the additional connections you will have. And those will be the additional weights and biases that you will have. And then do the same thing. So exactly same thing. The only thing that is additional here is the z here. The random parameter has been added and you are fine to go. We have actually done some work on this also, which is simulation-free reliability analysis, because you don't need any data, so you don't need to run any simulation. But that is not the focus of the talk today. That paper is on archive under review. So in archive, if you want to check, you can check that actually. So the same thing is shown here. I can skip this slide actually, but this idea is same, that you take some neural network, I mean, satisfy the initial and boundary condition, and then do automatic differentiation, and then you have your physics informed deep neural network. But in this case, we cannot use this, as our governing law is approximate. So if you cannot use this framework for the problem we are trying to solve. So direct application of this framework is out of the picture. So that brings me to the second part, which is some hypothesis. So we talked about physics informed. Some idea I hope you have now of physics informed, but we also know now that that cannot be used. So here is the first hypothesis, that approximate governing laws, obviously they are approximate, but even in that case, those are not useless. They possess some useful information, and we will like to exploit those information. So approximate governing laws, even if not exact, do possess some useful information, and we are interested in using those information. So now, first of all, what does learning means? Let us try to understand in the context of neural network. So when you are training a neural network, that is the learning phase. And during the training phase or the learning phase, what you do is simple. You update your weights and biases. So learning in deep learning means computing the unknown weights and biases. So in the process of learning, if you are gaining some knowledge, because when you learn, you gain knowledge, you become knowledgeable. So that knowledge is nothing but your weights and biases. So the weights and biases are the one that is storing those knowledges. This is a comparison between what happens in reality and a comparison with neural network. So now, second thing is transfer of weight and transfer of knowledge. So if we freeze some of these weights and biases, so we can say that we are freezing or retaining some of the knowledge that I have gained from previous, say from the physics. So basically, if I freeze some of the weights and biases, first of all, that means I am preserving some of the knowledge. So that was the third point, right? If we keep weights and biases unchanged, this is equivalent to preserving the knowledge partially, because there is a sum here, right? Transfer of knowledge. So when you train a neural network, in this case, so there are two types of transfer of knowledge. So this is another type. The other type will come later. So in this case, the transfer of knowledge is that suppose you have a governing equation. The governing equation poses some knowledge. Based on that governing equation, you are solving a problem, training a physics informed neural network, and computing the weights and biases. So we can say that the knowledge that the physical law has been transferred to the weights and biases. So that is transfer of knowledge one. So I should have written one here. There is another transfer of knowledge coming shortly. And then let us think of two examples. Say I don't know how to drive, and that is a reality. So if I start learning to drive today a car, I may take 7 days, 10 days to learn. Okay, in Delhi, let's say. But say some of you have learned how to drive in US, and that was I mean, you would drive on the right hand side of the road, right? So you come back to India. Now the system has changed. So you have to adjust, right? You will be able to adjust in a much smaller time as compared to the time that I will take to learn, because you are starting from a better basic. So knowledge gained. I mean, so the important point here is to start from a good starting point. If you are starting from a good starting point, you will be able to acquire knowledge quickly. And these are the things which may sound vague now, but will become clear in the next slide when we talk about the framework. So we are going to use most of this hypothesis and the terminologies that I used just now. So now let us come to the framework. So I have some governing equation which is approximate, and I have some data which is kind of high fidelity. So step one, what I will do is I will solve this governing equation along with the associated boundary and initial conditions using physics informed neural network. And if I do that, the knowledge from this approximate equation will be transferred to my neural network. So the neural network is now having some knowledge, approximate as it is, but some knowledge about the physics, which is approximate. So step two is I want to preserve this knowledge, but I also want to update it from the data. So since I want to preserve the knowledge, what I do is I freeze the weights and biases of all but the last few layers of the neural network. So I am preserving some of the knowledge. I cannot preserve all of the knowledge because then I cannot learn new things with the current setup. So that is the second step, that where we are preserving the knowledge. Step three, I want to again do a transfer of knowledge from data to neural network, which means now I have frozen the weights and biases of the first few, most of the layers except the last few layers. But for the last few layers, I want to update. So this update I'm going to do using this data, because now this will basically fine tune my result. And lastly, I do want to do all of this thing quickly, specifically step three. So step three, when I'm starting to update in step three, I will start from whatever weights and biases I have learned in step one. That means that will give me a good base to start from. So that is like I already know how to drive. I'm just adjusting myself to the Indian context. So, and that will help us in faster convergence. The optimization algorithm of or the optimization routine will converge really fast. And these are the three steps. And fourth one is basically the added thing we do, and that is your multi-fidelity physics informed neural network, because the finally trained network is learning from multi data and models of multiple fidelities. It is having some information about the physics, and yeah, and that's why it's a multi-fidelity physics informed neural network. So here is the idea, in the same idea in a schematic form. So first what we do is DC here is not my data point. These are my collocation points. So I generate collocation points for the input, and then for that I train my neural network. I don't use a boundary loss term, but instead I modify my U, the neural network output, in such a way such that the boundary condition is automatically satisfied. This is an old mechanics trick, nothing new. And then using this U, I represent my residual, which I'm going to minimize. And I minimize this thing using physics induced, or I minimize this using physics informed framework, which I discussed earlier. So this is my low fidelity training phase. And I do that. Once that is done, so I have computed my theta L, which is my neural network parameter. I move to the high fidelity phase. Here I have my data, and among the parameters you see, I'm only updating theta t, which is in this case the last layer, but it can be more than that also. And the yellow ones I have fixed it, so they are frozen, they are not going to change. This is the only one that is going to change from this data, and I basically train it. Since I have assumed my boundary condition to be exact, they are here, but you can remove them, it will not matter. We have tried that out. And this is basically your high fidelity training phase. Obviously, when you are updating theta t, you start from whatever theta t was computed here. You start from whatever theta t was computed here. So that is basically the whole framework. Now, this framework has different component, right? This framework has different components. One of the component is obviously transfer learning part, whether it can actually learn from multi-fidelity kind of thing or not. And the second is obviously physics informed and that part. So therefore, we created two sets of problem. Problem set one is basically the validation of our transfer learning framework only. So there is no physics here in this case. We just want to validate the transfer learning framework for multi-fidelity case. And in that case, we took two problems. In problem one, ULX is basically my low fidelity model. There is no physics, so plain equation. UHX is my high fidelity model. And in problem two, again, you have UL and UH, and those are your low fidelity and high fidelity model. Now, one of the question open challenge in neural network is how to determine the neural network architecture. Generally, it is done in a trial and error fashion. There are some work on adaptivity which we are currently doing, but that is not yet published. But right now it is trial and error, and based on trial and error, we fix the network architecture. Sigma, there was a nonlinear activation function. So the most popular one is the ReLU one, which is rectified linear unit. That means it is linear if x is greater than 0, otherwise it is 0. That is what we use here. Training data. So in this case, there is no physics. So I have low fidelity data and high fidelity data. So I have 11 low fidelity point, 5 high fidelity point in this case. For problem 2, I have 51 low fidelity point and 16 high fidelity point. And I need to optimize. So you need to use some optimizer routine. So we use two optimizers. First, we run the RMS prop, which is a variant of stochastic gradient descent proposed by the famous Jeffrey Hinton during a class lecture actually. So he was taking a lecture where he came up with this idea and proposed it there itself. And we use it in both the cases. OK, so the objective with these two problems is to check whether transfer learning works or not. Transfer learning means freezing the weights and only updating the weights of the last few layers. So that was transfer of knowledge part 2, right? And here are the results. So the exact solution is in red. We tried training with only the high fidelity data, and you can see it is performing very bad, the black one. And then we tried multi-fidelity framework, but with different transfer learning layer. So TL1 means during the transfer learning phase, only the last layer is getting updated. In this case, last 2, last 3, and last 4. So that is what is happening here. And obviously there is A, B, and C, which are these values which are shown there. Problem 2 was a nonlinear mapping, so this was more challenging. And you can see that in this case, we did not perform the case study. We directly used last 2 layers. And you can see that the match is quite good, not exact by any means, but quite good. And significantly better as compared to the high fidelity one. OK, so this was the transfer learning validation. Let us go to the second part, and this is the real part actually, where we basically illustrate how it can be used for reliability analysis with physics and data. So problem 1, a benchmark problem solved by many in the domain of and so we took it because the results is well known, and it is always good to validate with some actual result which is available. So a simple diffusion equation. This is your initial condition, ODE, so no boundary condition. Z here is random, which is coming from a Gaussian distribution, and then you have these parameters of the Gaussian distribution, right? And then U0 is your threshold, and this threshold is for the limit state function. So basically, if UH is less than U0, that is a failure domain, right? So yeah. And then your high fidelity model is a function of the result that you get here. So you can compute your low fidelity UL, plug it here into the high fidelity one, and that is your high fidelity model. Now, for us, This high fidelity model is not available. We don't know the green. We don't have this. We don't know this. What we have is data point from here. And data only at 3 points, starting, ending, and the middle one. So actually, practically at 2 points, because the starting is the initial condition always known to me. That is step 1. Step 2, this physics is known to me. So, and that's it. So this is what is known to me. And I want to compute this probability of failure. So first of all, we try MCS, right? We try MCS. And in MCS, the results is there. This is the gold standard, the benchmark result. So we compare with respect to the MCS result. And you can see that in MCS, this is the number of points that is needed. NH is the number of simulations. And for each simulation, we have run it at 1001 time steps. So that is what the number of points mean. Then we tried MF-PIDNN, which means low fidelity physics informed deep neural network. That means forget about the green box, only concentrate on the maroon box and try to find it out. And if you do it, obviously this is not correct. So you get a very bad result, almost 152.5% error. So this is not exact. Second, you can try only with the data. So how many data you have? You have 15 times 3, so 45 data points. So 3 is your time step and 15 is your number of stochastic variables, Z. So 15 samples of that. So you run actually 15 simulations, but you get 45 points. And even in that case, you can see it is performing very bad, 30%, close to 30% error. And then when you come to the combination of two, that is the proposed framework, the error is in the order of 3%, which is significantly less as compared to the other two. And obviously, it can be improved. You increase data, this will improve, but we did not show that. Yeah, actually we showed it. Sorry. So, and then we showed that what happens when you increase the number of samples. So for this stochastic variable, and we see that green one is actually your MCS result, and at 20 actually it matches exactly. At 15 there is some small difference, as you can see, and yeah. Okay, so that was problem number 1, a simple ODE. In problem number 2, we took the Burger's equation. The reason is this has been previously solved using physics informed. And this has some challenges. Some shock waves are generated in this case. If you see at x equal to 0, there are some shock waves generated. And not only that, this is, I mean, you will see that there is a transition layer in this problem, which is super sensitive to the stochastic variable. So this is like, it's very difficult to solve. I mean, this may look a small problem, but you try to approximate it, it's very difficult. So yeah, so here you have your high fidelity model. So this is the actual Burger's equation. You don't know it, so this is not known to you, but this is the high fidelity model, which is hidden from you. You don't know that. Delta is your stochastic variable, and it is uniform in 0 to 1. And then your limit state function is of this form. So it is defined by using Z, and Z is my transition layer, which you can find out by solving this, and basically where it is transitioning from positive to negative. And then my low fidelity model you see here. So I have considered 2 low fidelity model. Actually, both are same, not different. So this new 0 value in the first case has been taken to be very, very, very small. So that means it is going. So if you look into, sorry, not little correction here, not new 0 to be small. So what we have done here is you see here UHT plus UH. So here you can assume a constant A. And that in the first case, that A has been taken very small, so small that the nonlinear term is almost irrelevant. It is not there. So in that case, your equation is kind of a low fidelity linear model. And in the second case, what we have done, and this is perhaps a little bit more interesting, we did it during the review phase. The reviewer asked for it, which is the new, which is my viscosity, kinematic viscosity, that has been taken to be, that we have taken a different value. So for the low fidelity model, we have taken a higher value of kinematic viscosity. And in that case, the viscosity, with that viscosity, it is an easier problem to solve. And for the high fidelity, we have taken a viscosity which is very small. So naturally, the transition is very fast, and there is a sharp change in the gradient, which is very difficult to track. Here are the results for the two cases. MCS results, again, my benchmark. In this case, there is both spatial and temporal discretization. So 33 spatial points for the first case C1 and 10 to the power 3 steps for the temporal domain. And then 10 to the power 4 simulations. So MCS and your results is 0.2. You try solving it using low fidelity, which is this model, which is a linear model, and naturally you get garbage, which is basically 0. So it is saying that your system is not going to fail where there is a 20% chance of failure, which is quite high by the reliability standard. You try using high fidelity with only data points, and you can see here like 120 data points, but actually 5 simulation run. So you are running the simulation 5 times and then 3 spatial point and 8 temporal points, and you get almost 100%. Like it is certain to fail, something like that. And 280% is the error in the reliability index. You go to multi-fidelity, well, the error is 8.5%. Going to the case 2, where the viscosity value is different. So you can see that nu naught is very high. So this is for corresponding to my low fidelity, and this corresponds to my high fidelity. Remember that the high fidelity model is not known to the neural network. It is only the low fidelity model that is known and the high fidelity data. So in this case, we use a little bit more points. So 6 simulations and 8 by 8 grid of space and time. And since we have more points, you see the high fidelity is now giving some reasonable results because of this high number. And multi-fidelity still is better, matching almost exactly with an error of 3% in this case as compared to MCS. Now, why is this result worse than this one? Well, data point is more in this case. So simple. Again, we performed some case study where we increased the number of training steps, number of T, and we saw that it is kind of converging at 6. So we saw that how the probability of failure is varying. Coming to the final problem, and this is actually a problem taken from biology, and this is basically cell signaling cascade, where so it is related to enzyme actually. So if you give an external stipulation, there are enzymes which are stipulated, and then so there is a dynamic equation. So this is taken from literature, well defined, and you can see this is a coupled equation, right? There are 3 equations coupled together, and there are many parameters here. You can see V max, K, G4, E3, and there are other parameters also. In total, if I'm not wrong, there are around 13 parameters in this case. 13 parameters in this case, and this is my high fidelity model. So actually, this is my model for both high fidelity and low fidelity. So what I do is simple. This IT value, you see, so for the low fidelity model, I take IT to be 0. What happens when IT is equal to 0? The first equation, you see it becomes decoupled. First equation is only function of E1 and E1. You solve it, substitute that E1 into your second equation. You can solve for E2 directly. There is no E3 there. You substitute E2 into third equation. You can directly solve it. So you can solve it sequentially instead of in a coupled manner. So that is my low fidelity model. For high fidelity, that is equal to 2. IT is equal to 2. And parameters are all having 10% variation. So this is my mean value, and then you can take 10% variation, and that is your uncertainty there. So here are the results. So MCS results are shown here. 10,000 times we have run the simulator, and this is a time-dependent ODE system of ODE. So 10 to the power 3 is the number of time steps we are considering. Low fidelity, you train directly from the physics, you get a 64% error, which is expected because IT is supposed to be 2, you are solving for 0. So that is expected. High fidelity, you train only from the data in specific 10 data points, and each having 5 points, so 5 temporal points, and you get an error of 98%, 100% error in beta. And then you go to multi-fidelity, and it's almost matching, right? The error is of 1.52%. There was this threshold parameter E3, 0. That's how we define the limit state function here. So we also tried varying the threshold parameter, and it performed exceedingly well. One more case study we did, and this is kind of more interesting. So I said we have 5 temporal points, right? These 5 temporal points were not equally spaced. So what we did was we spaced the 5 temporal points between 3 and 7. Okay, between 3 and 7. No, actually between 4 and 7, if I'm not wrong. We placed those temporal points. So that means this first result you are seeing, we tried to see how the method is performing when it is trying to predict the past, where I don't have any temporal data. And you see it is performing reasonably well. And then in the last case, what I'm showing here is basically how the model is performing when it is trying to extrapolate to the future. And even in that case, the results are reasonably well. Yeah, the other two are in the range, so they are expected to be good, and they are kind of good. So coming to the way forward, I mean, okay, so coming to the last part of the talk. So basically that was the framework. So as I said, this framework was developed when, I mean, this was kind of a thought that came into my mind when I was sitting idle in my home, doing nothing kind of. So obviously there are some limitations, right? First of all, the neural network architecture, you need to select it manually. This needs to be automated. So much more is desirable actually. Accuracy can be improved, like 2%, 3% error is coming, but you will probably want a more accurate result. Although, even though transfer learning seems to be a reasonable alternative to the multi-fidelity for solving multi-fidelity problems. There are other ways of solving, but all the ways of solving multi-fidelity depends on data. With transfer learning, you can bring physics into the picture with using the framework. Obviously, there are other ways of transfer learning, and we need to investigate how those things can be integrated and whether they can give better results. Real scale application is something that is missing. The problems were not really that high scale dimensional. Generally, we solve problems of 4,000 dimensions, 4,000 stochastic dimension. And that is actually a problem that a student from IIT Guwahati has done with me, and he's a UG actually. So he has already done that. But yeah, that was not shown here because I did not do that. I did not have the resources. And there are other ways of. So if we look into if you take a bird's eye view, what we are trying to do here is we are trying to fuse data and physics. And this is not the only way of fusing data and physics. One of the master student, who is now a PhD student with me, has actually developed another way of fusing data and physics. And that is perhaps another way of looking into problems, specifically for dynamical problems with better extrapolation capability. And there are other alternatives. It's not the only way. It's just the beginning of the path. There is much more that is desirable and much more that we should aim for. Everyone should aim for. So with that, I will conclude my talk. Thank you. I hope I have not exceeded the time. I think I'm on time. So thank you. And any questions you have, I will be happy to answer.
Thank you, Professor Chakraborty. It was a wonderful, wonderful lecture, and not really a lecture in a sense. It was like a transfer of knowledge. Learned so many things today, right? And you were very gentle while navigating through the difficult concepts, which was the high points, one of the high points of the talk. And may I now take this opportunity to open the question answer session. If there are any questions, maybe this is the time to ask. Yes, the participants in the meeting, I mean, could you please ask a few questions? You can raise your hands one by one and maybe ask a few questions. So far, I'm not seeing any hands being raised. Okay, there is Naveen Kumar, then Nikhil Mahar. Okay, Naveen, please go ahead.
Yeah, thank you, sir. Thank you, sir, for the presentation. So I'm new to this field of learning, so don't know whether the question is maybe right or not. So you have shown a high fidelity physics and a low fidelity physical model and a high fidelity and data. So can this be used for like medium fidelity physics model where we have medium uncertainty in physical model and medium uncertainty in the data field data that we are getting?
Correct. So no, this is a very relevant question. In fact, no question is irrelevant. So it's not like that. So yeah. So I was talking about multi-fidelity, right? But what actually I showed is bi-fidelity. So there are only two fidelities. One was low, one was high. In reality, it is not limited to that. You can have multiple level of fidelities. So think of a building or anything, right? You can have sensors, some very costly sensors, some medium costly sensors, and some are like you are going to the field and doing actual measurements. So like three kinds of fidelities you can have. So that can also be done here. In that case, you will have to do a tool. You have to do the transfer learning twice, from low to medium to high. The other part was what if both are like medium, right? Nothing is high fidelity. So in that case, what we can do? Let us see. So if you are not giving me any high fidelity data, in that case, the best I can do is give you results which corresponds to the medium fidelity and maybe some improvement by considering some noise in your data. That is the best I can do. I need to see some data which is of extremely high accuracy to actually do something there. If you don't show me anything, probably that will not work. But you can have multiple fidelities, definitely.
Thank you. Thank you.
So the next question is by next hand raised is Nikhil Mahar. Nikhil, please go ahead and ask the question.
Sir, I would like to ask, like, how can we incorporate like higher variables that we will face in high fidelity model, and like in low fidelity model, we have, suppose we have a cantilever beam and we want to get its crushing moment, and we have like a variable like our displacement, or sorry, force that we are given. And so that will be a low fidelity model. In high fidelity model, suppose we are assuming our support condition will not be purely fixed. They will be like two springs. So
Right.
in that high fidelity model, I'm incorporating another two variables like rotational stiffness and linear stiffness. So how can I incorporate those two variables in my input layers in low fidelity model?
Correct. So first of all, you have to think what you are mapping from. For example, in your the high fidelity model is my data, right? And probably what you are trying to map is from force to displacement. The data already have that information. You are generating the data by incorporating those knowledge into your FE model or from your actual simulation, or I mean actual experimental result. And the data is having that information. The displacement that you have got in the high fidelity model is actually based on those assumptions. So the data is already having that information. But a more difficult question, so to take it a little bit away, that what if that is my now random parameter? So in my high fidelity model, there is one or two more random parameters. So now I cannot say that the data is embedded because I need to model it. In that case, this will come under a category which is known as stochastic simulator. You have to think of it as a stochastic simulator where some of the parameters are uncertain, other parameters are also uncertain, but you don't have knowledge, and you have to model it as a stochastic simulator where even if you give the same input, your model will give you some different input. So I will suggest that you search for stochastic simulator or surrogate model for stochastic simulator in that case, in the second question. And if you're asking the first question, then there is no change is needed because I'm anyways trying to map from F to delta. So mapping is same and the delta has the information, right?
Okay,
So now I have our respected head of the department, Professor Gokhale. He has raised his hand. He wants to ask a few questions. Professor Gokhale, please.
Thank you, Dr. Hazra. Dr. Souvik, good evening.
Good evening.
Yeah. I hope your interaction is going well. I had to leave in between for some time. I'm joined back. Look, I do not understand either structural engineering or even machine learning, that is physics informed something that you have presented. But I just I was just curious to know, you take up some engineering problem, right? and apply your physics informed neural network, and also apply our conventional neural network approach, right? Would you see some difference in that? And if it is, particularly in what? I mean, your physics informed neural network would deal with the stochasticity better, or the conventional neural network would deal with it better, or in what sort of basically advantage you're getting, because both are essentially database, right? In addition to that, there are some more things which you take into account in case of physics informed neural network.
Okay. So thank you for this question. Really nice question. So let me try to answer this. Not everything is good about physics informed. So let me start with the disadvantages of physics informed. Training physics informed is very difficult. If you have data training, that is very easy. Physics informed, the loss function is really difficult, and it's very difficult to train it. Data driven, it's much easier. But that's it for the advantage of data driven. So now coming to the physics informed. Stochasticity is a domain I work on, but this concept is not limited to stochastic problem. So let us first think of problem where there is no uncertainty or stochasticity. So if you are training using the physics informed, that means your neural network is satisfying your governing physics in some sense, not exactly, but in some approximate sense. And this allows you to extrapolate. So if you want to extrapolate to unseen environment, future time, physics informed allows you to do that. Data driven, if you have data from 1 to 10 seconds, if you're trying to predict 100 seconds, well, that is almost next to impossible until and unless you do some manual tuning and manual architecture design so that it matches. For example, the response is supposed to be sinusoidal and you make your activation function sinusoidal. But that is not really a neural network. If you know the answer, why will you use that? So generalization is what physics informed gives us, data driven lacks. And coming to the stochastic part, there is one more advantage with physics informed. When we do talk about reliability or those kind of problems, specifically using surrogate models, data generation is a big challenge. So if we are solving a real, say, a building problem or a bridge problem or an environmental problem having thousands of degrees of freedom, and if you want to generate, or maybe millions of degrees of freedom, and if you want to generate data for that, well, very difficult problem. I mean, very difficult to generate data. For example, the wind turbine. I mean, if you were thinking of generating data using DNS, you will not be able to generate enough data. With physics informed, those data is not needed. And if your physics informed loss function is not actually converging, okay, you go ahead and generate few data that will help in regularizing the solution. So data efficiency is another advantage of physics informed. You don't really need data. And even if you need it, is very, very less. So these are the two advantages. But having said that, at the end of the day, we should aim for, and that is what I am aiming for, is a domain where there is both physics and data. Because physics has its limitation, data has its limitation. And we should try to bring the best of the two. And that is what I am aiming for, at least. I don't know how much successful I will be, but that's what the aim is in this work and also on other works that we are doing.
All right, thank you. I mean, that's what I was thinking, because non-linearity, is the basic attribute, or the neural networks, deal with non-linearity better. So in physics informed neural network also, that particular attribute will be retained as it is, right? So in addition to that, yeah, in addition to that, what exactly you're getting, that is what I was interested in knowing. Thank you for your answer. Thank you, Dr. Souvik.
Thank you.
Dr. Hazra, over to you.
I have one more question, maybe the last one, which I'll take because the session is getting longer now. So, Professor Arunasis Chakraborty, right? So, as Dr. Souvik Chakraborty mentioned that he had very special connection with Professor Arunasis Chakraborty. So, I will let the two of you to interact with each other. Professor Arunasis Chakraborty, please.
You are muted.
Professor Chakraborty, you are muted. Can you can you unmute yourself and ask the question?
Yeah. Thank you, Dr. Hajra, and see you, Professor Chakraborty, again back after a long time.
Yeah, 2018,
nice.
I think. Let's meet.
Yeah. So it was a really nice presentation, and I have one or two questions. Actually, I have a couple of, but again, because of the limitations, I'll just. In fact, one of the question I was thinking to ask you the dimension of the problem, which you have already informed, and you have already solved a really large dimension problem. That's your proposal is really interesting. The way you actually start with a kind of approximate model and use that information further with the additional inputs that you have. That's really interesting. In fact, I just wish to make a comment, even for example, say in Kalman filter also, if you do, we use the same approach in some way, because you start with some approximations and then use that information, retune the filter again. So that way, really nice to see. But one thing actually I wish to know, so far the computation is concerned. So if you follow this approach, and you already said that you need a very special kind of computational techniques and the architectures, okay, which is not always available. So that way, how long actually it takes to train and just come to a conclusions, if you can throw some light.
Okay, so yeah, we need GPU. Otherwise, although these problems I have solved, it can probably be solved on CPU also, but generally we need GPU. In most of the problems, even the 4,000 problem, that 4,000 dimensional problem that we solved, in that case we used one GPU, Google Colab, so not even a real HPC, cloud computing, and it takes around 15 to 20 minutes to train. So training time is in that way. Having said that, it obviously will depend on the number of parameters we had. So in our model, we have around 1 lakh something parameters. There are models which are having 14 million parameters, which Google is doing, right? But they can afford to do that. They have the best supercomputers. The best, but I mean, and this is a challenge, or this was a challenge, and that is why probably everyone is trying to encash this thing. So Amazon Web Service, you can buy those things. Every IITs have now, I think, HPC, and there is GPU clusters there, and you need those things. You need to explore those things. If you're trying to do it on your laptop, then it may not be possible. Yeah, definitely. Training part, prediction is you can do it anywhere. So, but training is the challenging part. Yeah.
Yes. And regarding this, one more, because some of the applications are having real-time issues, right? So if you try to extend these from offline to online, is it really possible? Can you just comment on that?
Yes. So even in deep learning, I have not worked on it, but there is a domain known as sequential learning, where you can have a pre-trained model, but now as data is coming, it will update based on that one data every time. And this is what we generally used in even reinforcement learning, which I'm trying to use now actually, where we have a reinforcement learning model which is trained, and there is a totally different concept. But the idea is that we try, based on the reinforcement learning, we predict for the next 10 time step, because it may be very 0.001, right? Say earthquake kind of thing. So 10 times step, that will allow us some leverage. So we can leverage that's a control kind of problem. And there, that 10 time step, we are predicting 10 step ahead so that we get that time to update our model. Always predict 10 step ahead and try to do it. And reinforcement learning can do that. Yeah.
Great. Well, I have many more, but I think let us close more.
Yeah.
Okay.
We'll definitely have more interactions.
Yeah, we can always talk later.
Of course. So, yeah, I will, if it is possible, then maybe even in a future date, I will invite Professor Chakraborty for another talk. Because he's so generous. Not everybody is generous to offer their time for talks like this, but he is very generous. So we will utilize his generosity, right? Since this talk was organized on behalf of ACE, that is Association for Civil Engineers, may I request our respected head of the department to just offer a vote of thanks and just quickly highlight, that we at ACE are extremely keen on doing such arranging such talks for the general audience and also for the students. So it will be really nice to hear one or two sentences from you, Professor Gokhale, if you please.
Yeah, all right. Yeah. So I would like to thank first the ACE and the team that is working for organizing, such talks. We actually need to invite people like Dr. Souvik for delivering talks on such interesting topics. I think became HOD in the month of February. Since then, I think there was no activity I observed in S. This was, I think, the first lecture. So I was very keen to join and know how things are done. Right. So I think it went well. It was quite impressive. And I like to thank Dr. Souvik Chakraborty for sparing his valuable time and enlightening our students with, the knowledge of a very, very different, domain, which I'm not sure whether our structural engineering students or any other, came across, this kind of, work, which are nowadays, becoming popular, and more researchers, coming forward working on it. So I look forward to many more activities under ACE, Dr. Hazra, and also, Dr. Souvik. I mean, this is just, kind of an introduction lecture. Maybe when you, start getting some interesting results, you are always again, welcome to share, if you would like to share with our students, with our, faculties who are interested, in knowing. Thank you very much, all of you.
Thank you.
And thank you, Professor Gokhale. I would certainly look forward to some of your discussions. In fact, it was one of the things in my agenda that I will request for a short meeting with you as to how to revamp ACE and bring in newer ideas as to how we can enrich, make it a more powerful medium than what it is at the present point of time. And with this, I would like to thank all those who have attended the talk today. It was a wonderful talk, and in many sense, I hope a lot of you realize this, and those who don't, for them, I would like to say that this topic, this area, this is actually now, it is going to take off. And if you can catch it now, or maybe, in a year or two, you will be, left gasping at it and said, okay, I missed the train. So this is one of those areas, the physics informed machine learning, right? So with this, I would close the session. I cannot thank you enough, Dr. Chakraborty, but it is customary on my part to just express the gesture of thanks, but these are empty gestures. I wish I could have given you some gifts from on behalf of ACE, but then
Okay.
In the virtual world, I'm not sure how I can do that. But upon HOD's as per his suggestion, that we will invite you again later, because this was such a wonderful talk.
Thank you,
Okay.
everyone.
Yeah, and with this, I'll close the session. Thanks all of you. Good evening. Bye bye.